up to 10 volts. Logarithmic amplifier. Logarithmic amplifier is designed by using a diode with operational amplifier. The practical circuit of a logarithmic amplifier is like this. The condition for using this circuit as a logarithmic amplifier is that this diode must be always in forward bias. If a diode is biased in forward direction, the current through diode, that is forward current IF, is given by the equation IF equal to I naught into e raised to power Vd upon eta Vt minus 1. This particular term is a positive exponential whose value will be very greater than this one. So IF will be equal to I naught into e raised to power Vd upon eta Vt. This one can be neglected. And this Vd voltage is the forward drop across the diode. And this Vt is the thermal voltage or volt equivalent of temperature, which is given by T upon 11,600, where T is temperature in degrees Kelvin. If we take T equal to 300 degrees Kelvin, then Vt comes out to be 0.0256 volts, which is equal to 25.6 or nearly 25 millivolt, or sometimes it is taken as 26 millivolts, where eta is ideality factor and it is equal to 1 for germanium and equal to 2 for silicon. So this equation will be used in the analysis of this logarithmic amplifier. We'll mark the voltage forward drop across the diode and we'll start the analysis. The analysis will be similar to the circuits which I have already seen in the previous chapter. At this point, the voltage Vp equal to 0 volt and the voltage Vn at this point due to virtual ground process will be equal to Vp equal to 0 volts. Now we will mark two currents, or we will apply KCL at this point. Vn will mark the currents. This will be the current through diode, that is forward current of diode, and this is the current I, and one current will be through the input terminals of op-amp, but we know that input resistance of op-amp is very high and this current will be 0. So now we'll apply KCL at Vn. If you apply KCL at Vn, there are two currents, both are taken outgoing current. So total incoming current should be equal to total outgoing current according to KCL. So total outgoing current IF plus I is equal to total incoming current, that is 0. Now IF is the forward current of diode which is already derived here, I naught into e raised to power Vd upon eta Vt. So this equation will be substituted here, I naught into e raised to power Vd upon eta Vt plus the current I is the current through this resistance R, which will be written as Vn minus Vi divided by R equal to 0. Now solving this equation, we get I naught equal into e raised to power Vd upon eta Vt plus this Vn equal to 0 volt. So this the whole term will be written as minus Vi upon R. Now in this circuit we know that this voltage Vd is the difference in potential at the two ends of the diode, and this Vd can be written as Vd equal to this voltage Vn minus this voltage V naught. We know that Vn equal to 0 volt, so Vd equal to minus V naught. Now substituting this part here, so I naught into e raised to power minus V naught upon eta Vt will be equal to Vi upon R. Now e raised to power minus V naught upon eta into Vt will be equal to Vi upon I naught into R. So now taking log on both sides, we know that this exponential term itself is an antilog. So after taking log, this term will be equal to minus V naught upon eta into Vt will be equal to log to the base e Vi upon I naught into R. And now the final expression of the output will be equal to minus eta into Vt log to the base e Vi upon I naught into R. So now we can say that V naught is V naught depends on the log of input voltage, so it is a logarithmic amplifier. This logarithmic amplifier can also be designed by using transistor in place of diode. Suppose we have this NPN transistor. This NPN transistor can be made to operate like a diode by shorting one junction, that is collector junction. If we short this collector junction of a diode, if you short this collector junction of a diode, this of this transistor can be made to work as a diode. This diode will have a voltage VB, only this junction will be operated, and the equation for collector current IC or IE both are nearly equal. The equation for collector current IC or IE will be equal to ICO into e raised to power VBE upon eta into Vt. This equation will be used for collector current or emitter current for this transistor. This is diode operated transistor. Now we will use this transistor in the circuit. We have shorted this collector and base terminal of transistor, and one more way is to use this transistor as a diode is to keep both base and collector at the same potential. So now we will use this transistor in place of diode. Now we have this transistor here, base is grounded, and as this non-inverting terminal VP is grounded, then by virtual ground process Vn will also be at zero potential. So here base and collector are at same potential, so this diode can be used, this transistor can be used as a diode. Here we will have two currents, this current IC and this current I. Again we will apply KCL at this point, so IC plus I will be equal to 0, and for IC we will put the expression IC equal to ICO into e raised to power VB upon eta into Vt, where sorry, there will be no eta in this expression, where Vt is the thermal voltage and ICO is the reverse saturation current of a transistor. Now, like in the previous case, we have substituted the value of Vd. Here we will substitute the value of Vb. We know that this Vb voltage is the difference in potential at this 2 point. So Vb can be written as Vb equal to 0 volt, which is the potential at the base terminal, minus V naught. So Vb equal to minus V naught. After solving the entire expression, we will get the expression of V naught equal to minus Vt log to the base e Vi upon ICO into R. This will be the final expression of the output. So again, output is depending on the log of input, so it is a logarithmic amplifier. Now, next circuit is anti-logarithmic amplifier or anti-log amplifier. Anti-logarithmic amplifier is also designed using diodes and transistor. The position of diode will be little different here. Diode will be connected at the input side, and this will be the feedback resistance RF. Now here also the voltage across diode will be equal to Vd, and the voltage Vp equal to 0 volt, clearly seen it is grounded. By using virtual ground process, Vn equal to 0 volt. Now we'll start the analysis. At this point we will be applying the KCL. One current will be I and other current will be IF. We know that at this point Vn, one current is approaching and other current is leaving. So when we apply KCL at Vn, when we apply KCL at Vn, one current is approaching, that is I, other current is leaving, that is IF. For this current I, will write the forward current equation of the diode, that is I naught into e raised to power Vd upon eta into Vt equal to, the equation for RF will be Vn minus V naught divided by RF. We know that Vn equal to 0 volt, so I naught into e raised to power Vd upon eta into Vt will be equal to minus V naught upon RF. Now this Vd can be represented in terms of Vi. This Vd is the voltage across the voltage difference between these two terminals. So Vd can be written as Vd equal to Vi minus Vn, which will be equal to Vi because Vn equal to 0 volt. So substituting in this expression, I naught into e raised to power Vi upon eta into Vt will be equal to minus V naught upon Rf. Now expression for V naught equal to minus I naught into Rf e raised to power Vi upon eta into Vt. Now this exponential term is itself an antilog, so V naught will be equal to minus I naught into Rf into antilog of Vi upon eta into Vt. So this amplifier is working as an antilog amplifier because output is depending on antilog of input. Now antilog amplifier can also be designed using transistor. We are using here PNP transistor. The analysis here of the circuit will be similar to the previous one. So remember this circuit, using transistor we have designed an anti-log amplifier. Now we'll solve some examples from gate examination. In the op-amp circuit shown, assume that the diode current follows the equation I equal to Is exponential of V upon Vt. For Vi equal to 2 volt, V naught equal to V naught 1, and for Vi equal to 4 volt, V naught is equal to V naught 2. The relationship between V naught 1 and V naught 2 is this circuit is given in the example, and the options are V naught 2 equal to root 2 into V naught 1, V naught 2 equal to e raised to power 2 V naught 1, V naught 2 equal to V naught 1 into ln of 2, and option D, V naught 1 minus V naught 2 equal to Vt into ln of 2. We'll start the analysis. We know that the voltage across this diode is V. According to the given expression of I, that is forward current of diode, Is is the reverse saturation current, V is the voltage across the diode. Now we'll start the analysis. Before that, we will derive the expression for V. V is the voltage at this point, that is Vn minus V naught, and we know that as Vp equal to 0 volt, Vn equal to 0 volt, so V equal to minus V naught. Now at this point we will be applying the KCL. One current will be I, other current will be If. We have taken one current incoming and other current outgoing, so incoming current should be equal to outgoing current according to the KCL equation. Incoming current equation is Vi minus Vn divided by 2 kilo ohms equal to If diode current, which is equal to Is e raised to power V upon Vt. Now Vn equal to 0 volt, so Vi upon 2 kilo ohms will be equal to Is e raised to power minus V naught by Vt, because we know that V equal to minus V naught. Now according to the given condition, if Vi equal to 2 volt, V naught equal to V naught 1. So substituting this, we get 2 volt by 2 kilo ohms equal to Is e raised to power minus V naught 1 by Vt. This will be first expression. Now the second condition is given as if Vi equal to 4 volt, V naught is equal to V naught 2. So 4 volt by 2 kilo ohms will be equal to Is e raised to power minus V naught 2 by Vt. This will be the second expression. Now dividing both the equations 1 and 2, 2 volt by 2 kilo ohm divided by 4 volt by 4 2 kilo ohms will be equal to Is into e raised to power minus V naught 1 by Vt divided by Is into e raised to power minus V naught 2 by Vt. This 2 kilo ohms will be cancelled out, so this will come out to be 1 by 2. Is will be cancelled, and this will be e raised to power minus V naught 1 by Vt divided by, and this can be taken at the top, or we will keep it here. So this can be taken in the numerator by cancelling this negative sign here, and it can be written as e raised to power V naught 2 divided by Vt. Now 1 by 2 will be equal to, after multiplying these two, we will get e raised to power V naught 2 minus V naught 1 divided by Vt. Now taking log on both sides, we get V naught 2 minus V naught 1 divided by Vt equal to log to the base e of 1 by 2, or it can be written as minus log to the base e 2. So now V naught 2 minus V naught 1 equal to minus Vt log to the base e of 2. And now if we reverse the order of these two, we'll get V naught 1 minus V naught 2. For that we will have to cancel this minus sign, we'll get log to the base e of 2. This is the final expression required, hence option D is correct. Now we'll solve one more example. In the circuit shown below, what is the output voltage V out if a silicon transistor Q and an ideal op-amp are used? The given circuit is now in the circuit we have to calculate the output voltage. The given options are minus 15 volt, minus 0.7 volt, plus 0.7 volt, and plus 15 volt. Looking at this circuit, it can be easily identified that the given circuit is a logarithmic amplifier which is designed using a transistor in place of diode. And for this transistor, this voltage VBE can be calculated as VB equal to the voltage at the base terminal, which is 0, minus output voltage V out. So V out equal to minus VBE in this case. If V out equal to minus VBE, we know that for a transistor VBE, for a silicon transistor, when it is in active region, VBE is equal to 0.7 volt. So the correct answer is minus 0.7 volts. Now we'll solve some general examples. Calculate the input impedance of the operational amplifier seen through the source, and the circuit is given as we have to calculate the input impedance seen through the source Vs. This input impedance is to be calculated. We know that the input impedance of an operational amplifier is very high and it is already considered as infinite. But here in this example, we are asked to calculate input impedance seen through this source Vs. The input impedance can be calculated as the ratio of voltage applied by the current supplied by this voltage source. This will be the input impedance of this operational amplifier seen through the source Vs. Now this current Is can be calculated as Is equal to the source voltage Vs minus Vn divided by 10 kilo ohms. This voltage is Vn. We know that voltage Vp equal to 0 volt because non-inverting terminal is grounded. So according to virtual ground process, Vn is also equal to 0 volt. If Vn equal to 0 volt, then Is equal to Vs upon 10 kilo ohms, and now Vs upon Is, which is our input impedance, is equal to 10 kilo ohms. So using this equation, this ratio, we can obtain this input impedance of the operational amplifier. Current to voltage converter. Current to voltage converter. In some applications, it is required to be to convert the input current into a voltage. This operational amplifier can be used for this purpose. The circuit will be like this. This is the input current source Is, and this is feedback resistance Rf. We know that in this circuit the non-inverting terminal is grounded, so Vp equal to 0 volt. Now as Vp equal to 0 volt, according to virtual ground process, Vn should also be equal to 0 volt. Now we'll start the analysis and we'll calculate the expression for output. Now this current Is will be coming through this branch, and as the current through input terminals of op-amp is 0, so the current Is will flow through this branch. means current is will be equal to if. As current is equal to if, for this if we can put its expression as if can be calculated as if equal to Vn minus V naught divided by Rf. And we know that Vn equal to 0 volts, so if equal to minus V naught upon Rf. Now we'll substitute is in place of if, so is will be equal to minus V naught upon Rf, so V naught equal to minus is into Rf. This is how a current is converted into a voltage. So this circuit gives an output which depends on output voltage which depends on the input current. So V naught equal to minus is into Rf. This is a current to voltage converter. Now next is voltage to current converter. Voltage to current converter. The circuit we have already seen. This is just like an inverting amplifier. In this inverting amplifier, we have to calculate the current flowing through this resistance, which will be called as load resistance, load current. Remember one thing, that a load resistance is a resistance which is connected to between output terminal and ground. This will be called as load resistance. Similarly here, this RF is connected in between output terminal and a ground, but this ground is not a physical ground, but this is a virtual ground, because only the potential at this value is 0 volt, but it is not a physical ground. So this RF in this circuit is called as floating load, because one end is not grounded. Floating load. So this is a voltage to current converter with floating load. Now we'll apply KCL at this point. We'll take one current I incoming and other current IL is also incoming. So applying KCL at Vn. If we apply KCL at Vn, two currents both are incoming, so I plus IL, there is no outgoing current, so it will be equal to 0. Now I can be written as Vs minus Vn divided by R1, and we want to calculate the expression for IL, so it will not be substituted as Vn equal to 0 volt, so Vs upon R1 plus IL equal to 0. This will give IL equal to minus Vs upon R1. So this is a voltage to current converter with floating load. Now we'll see the voltage to current converter with grounded load. This will be the load resistance, and we want to calculate the load current IL through this load resistance. Now we will calculate the value of this load current. This is the source voltage Vs. Now we'll start our analysis. First we will apply KCL at this point Vp. This is voltage to current converter with grounded load. Now applying KCL at Vn will mark three currents I1, IL and I2, and in the fourth branch the incoming current in the uh, the current in the input terminal of op amp will be 0, so there will be no current in the fourth branch. There are only three currents. All the three currents are taken outgoing, so total outgoing current should be equal to total incoming current, which is 0. Now expression for I1 can be written as I1 equal to Vp minus Vs divided by R. For I2, Vp minus V0 divided by R plus load current IL equal to 0. Now this can be further simplified as Vp upon R minus Vs upon R plus Vp upon R minus V0 upon R plus IL equal to 0. Now 2 Vp upon R minus Vs upon R minus V0 upon R plus IL equal to 0. Now this will be our expression number 1. Now we'll apply KCL at this point Vn. Now if we apply KCL at this point Vn, we'll mark two currents, both are outgoing, I2 and I3. I3 and I4. At this point both the currents are outgoing, so I4 plus I3 equal to 0. There is no incoming current. For I3 the expression is Vn minus 0 divided by R. For this will be I3 and this will be I4. For I4 the expression will be Vn minus V0 divided by R will be equal to 0. Now simplifying this expression we get 2 Vn upon R equal to V0 upon R. Now we know that Vp equal to Vn, so 2 Vp upon R equal to V0 upon R. Now this expression will be substituted in expression number 1. If you substitute it here, so V0 upon R minus Vs upon R minus V0 upon R plus IL equal to 0. This V0 by R will be cancelled out, so IL will be equal to Vs upon R. So the output load current depends on input voltage, so it is a voltage to current converter with grounded load. Characteristics of op amp in open loop configuration. We'll see the op amp as a comparator. Suppose we have this op amp with input voltages V1 and V2. V1 is the input voltage at inverting input and V2 is the voltage at non-inverting input. We already know that the output generated by this operational amplifier is the difference in the amplification of the difference in the voltages at the input terminals, that is AOL into V2 minus V1. And these are the two power supplies, plus VCC and minus VEE. Now we know that for an operational amplifier, if it is an ideal operational amplifier, then for ideal operational amplifier, open loop gain is equal to infinite. And we know that V0 is equal to AOL into V2 minus V1. If V2 is greater than V1, the difference may be slight or large. If V2 is greater than V1, then this term will be positive. V2 minus V1 is equal to positive. If V2 minus V1 is positive, then it will be multiplied with infinite, and V2 V0 will be equal to plus infinity. Similarly, if V1 is greater than V2, then V2 minus V1 will be negative, because this time V1 is greater than V2. And if V2 minus V1 is negative, then this negative term will be multiplied with infinite, and output voltage will become minus infinity. Output voltage will become minus infinity. Now we'll draw all these things on a graph. The y-axis represents output voltage and x-axis represents the difference in the input voltages, that is V2 minus V1. This axis represents the positive values of V2 minus V1, means if V2 is greater than V1, then we will be plotting on this axis, and if V1 is greater than V2, we'll be plotting the graph on negative x-axis. Now if V2 minus V1 is positive, for small difference, if V2 minus V1 is 0.01 volt, this much voltage, V2 minus V1 is 0.01 voltage, this value will be multiplied with infinite and output will become infinite, means here somewhere will be output for this point. But we know that for any circuit, it cannot produce an infinite voltage or infinite output, because for the operation of this circuit we have applied these two voltages, VCC and VEE. These are the biasing voltages. If we remove these two voltages, this operational amplifier will be of no use. So these two voltages are the voltages which are helping this operational amplifier to amplify the signal supplied at the input terminals. And as the output is trying to go beyond these two voltages, the output will be saturated below these two voltages, means the output voltage is going to infinite, but it will saturate at the voltage, saturation voltage, which will be always which will always also be called as plus Vsat. Now if we increase the difference, again this difference will be multiplied with open loop gain, and output will try to go to infinity, but again the output will be saturated to plus Vsat. In this way, for all the positive differences, the output will be plus Vsat. Output cannot go beyond this plus Vsat value, and this plus Vsat value is nearly equal to plus VCC, but not exactly equal to plus VCC. But in the examples, in the questions in the gate examination, this plus Vsat is considered equal to plus VCC. There is little difference between these two voltages. Now if V2 minus V1 is negative, we are applying negative difference. If difference is negative, then this negative difference will be multiplied with infinite, and in this case the output will be minus infinity. So for small negative difference, output will go to minus infinity, but we know that output cannot exceed this negative voltage, so it will saturate to a voltage minus Vsat. Now If we apply if we increase the difference between V2 minus V1, then for large differences again it will be multiplied with infinite, and the output will try to go to infinity, but it will be again saturated to minus Vz. So for these differences output will be like this. If we join all the points we get a graph like this. So now this is the transfer characteristics of ideal op-amp. So from these transfer characteristics I mean to say that an operational amplifier when operated in open loop condition, if non-inverting input voltage is greater than inverting input voltage, then output will always be plus Vset, and if inverting input voltage V1 is greater than V2, then output will always be minus Vset. These are the characteristics of operational amplifier in open loop condition, that is ideal operational amplifier in open loop condition. Now, what if we have a practical operational amplifier? For the practical operational amplifier, its open loop gain will be limited. Suppose this is an operational amplifier with voltage V1 and V2, and we know that for a practical operational amplifier its open loop gain AOL is around 10 raised to power 6. It is not infinite, and these are the voltages plus VCC and minus VEE. Now if we write the expression for output, it will be again same AOL into V2 minus V1, but there will be little difference in the characteristics. Again we will plot V2 minus V1 against V0. We'll start plotting this graph. If V2 minus V1, this difference is very small. If we keep this difference 1 microvolts, and if we keep these voltages at plus 15 and minus 15 volts, now if we have this difference is this difference 1 microvolt, this will be multiplied with open loop gain, that is 10 raised to power 6. Then after multiplication we will get output equal to 1 volt. So here the output will be 1 volt. Now we increase the difference. If we make this difference as 5 microvolts, then this 5 microvolts will be multiplied with 10 raised to power 6, and if we multiply this with 10 raised to power 6, we get output equal to 5 volts. Now if we increase this reference to 15 microvolt, then this 15 microvolt will be multiplied with 10 raised to power 6, and we get an output equal to 15 volt. Now if we make this difference equal to 20 microvolts, then if we multiply it with 10 raised to power 6, output becomes 20 volt, but we know that the supply voltage is up to plus 15, so output cannot exceed plus 15 volts. So for 20 volts also the output is 15 volts. Now if we join all the points we get a graph like this, and also in the negative direction we get graph like this. For ideal operational amplifier we got the graph like this. So here the difference in the transfer characteristics is because of gain of the operational amplifier. So if we required transfer characteristics like an ideal operational amplifier. Using practical operational amplifier, we will require to increase the gain of the operational amplifier by applying positive feedback. Here is the reason why we apply positive feedback to operational amplifier. The reason is simple. We want to get the transfer characteristics of ideal operational amplifier, which is possible only if we increase the gain of the operational amplifier, which is increased by applying positive feedback to the operational amplifier. Now we'll see one circuit in open loop condition, and after that we'll start the